Good morning, everyone. Welcome to the second lecture in Beyond Bitcoin. Today's lecture is by far the most technical one. So please don't be scared. Please don't be worried. Nicholas, Kavita, and I are here to answer any questions. You can either add them to the chat in Zoom or to the Slack channel. That way, if you add them to the Slack, even if we don't get to them during Nicholas's lecture, then later on we'll be able to answer all of them and also provide extra material. So we're here to help. Nicholas, are you all set?
Okay, great. So before we begin, some very quick administrative announcements for today. This year, just like last year, our class is oversubscribed. But the good thing is that since this year the lectures are happening through video, we were able to invite auditors. So today, as of today, auditors of the class are also participating through Zoom. That's why you guys see a lot more people in the room today compared to last time. This and potentially next would be the two most technical classes we will have in the class. The lecture was originally created for a computer science class that I designed, but don't worry, it was heavily adapted to get simplified and sometimes oversimplified to require zero background knowledge. The reason why we wanted to have these two lectures anyways, even if they may seem a little too technical for non-CS or technical student, is because there's a lot of aura behind Bitcoin, and that makes it sound more complex than it actually is. It's actually conceptually pretty simple, and all these obscure puzzles that need to be solved, all these weird, sometimes sounding concepts are actually very straightforward if we tell you exactly what they are. Having said this, I want to give you the agenda for today and next class. We'll be talking about the following 5 topics and potentially some advanced topics if we have time at the end. So the topics are the following: cryptographic hashes, which is a very important cornerstone of what's needed, a building block of blockchains. They are possible because of this. We're going to be talking about what is a block, what then becomes a blockchain. Then we will talk about how Bitcoin puts these concepts together. And then most likely in the next lecture, we are going to talk about the security of blockchain and the security of Bitcoin. Why can we have anonymous miners or nodes, as they are otherwise called, being those people who are processing our transactions and we still trust them? That is all possible because of those cryptographic properties that Bitcoin and blockchain is utilizing. So without further delay, let's start with the simplest of the concepts, hashes. So a hashing function is a function, just like in math, there's a function that gets as an input an arbitrary length of data. It can be a text file, it can be a block in a blockchain. And as an output, it produces a digest of those data into a specific size. What do I mean by digest? It's let's say, a string looking thing that always has exactly the same size. So no matter how big the data is, the data could be 1 byte. The hash of that data is still the same size. The data could be an entire video file that is giant. The hash is still the same size. So the function gets data and produces hash of those data. And an important property of this is that the same data will always result to the same hash. And one very popular such hash function, especially used by Bitcoin, is called SHA-256. It's 256 because the resulting hash has 256 bits, which if you translate it into hexadecimal digits, then you get 64 hexadecimal digits. That's why that's how it looks. And let me show you this with a specific example. So if I click on this, it will open this software, which is open source software that I adapted slightly for the purposes of today's lecture. so that it can emphasize the points that I wanted to make. And I will point a link to the source code. I did not write the software, just modified it. So here's, but I like it because it's very visual. So here's an example. If I put as data the letter A, then I'm getting a hash, this hash down here. If I change this, then the hash changes significantly. The entire hash is completely different. Even though my input is only by one character different, I didn't see one character change in the hash. I saw the hash completely changing. And let's go back to A to see that the hash is still the same. You see, the hash of A is 559, and go back to A, again 559, no matter what I do. And the data, as I said, could be arbitrary length there. Okay, it can be very long, and the hash is still the same size. Okay, now there is the concept that certain hashes are very secure, and that would be the content of the next lecture, where I will explain to you why this is important and how secure are they. But this property is making the blockchains essentially possible. But let's not jump to it just yet. Now, let's talk about blocks. To talk about blocks, I'll start talking a little bit about finance and ledgers. And let's introduce ledgers. So as you know from your finance classes, a ledger is essentially a spreadsheet of financial transactions. And why we're talking about ledgers is the fundamental facility of a blockchain is essentially a ledger, a decentralized ledger. So that's why we're talking about ledgers and explaining ledgers right now. So this a ledger could look like this. It's a list of financial transactions. At 5 p.m., Alice gave to Bob $1. At 5:01, Bob gave to Carol $0.50, and so on and so forth. They are transactions, and they have a timestamp. All right. So now, for arbitrary reason, without explaining why, I am saying instead of let's have a lower quality ledger here, and rather than storing the exact time of every single transaction when it happened, let's just say we're going to be storing transactions every 10 minutes, and therefore we're going to be okay that we lose this information of when each transaction really happened. All right, so if we're storing at 5:10, let me go back. We're going at 5:10, we have knowledge of these three transactions, so we can just store them as 5:10 as if all of them happened a few minutes later. And the same at 5:20, we have this transaction, 5:30, we have this transaction. Then it becomes like this. Okay, let's take now this concept one step further. And let's say that because all these transactions here at 5:10, all of them happened at 5:10, I don't need to store 5:10 on each one of them. And I'm just going to say that all of this happened at 5:10. And all of this happened at 5:20. All of this happened at 5:30. So I'm keep creating the concept in computer science terms. So for an arbitrary reason, I just split my transactions into different records. And I call the first one record 1, the second record 2, the second record 3. Rather than storing them in one big spreadsheet, each record, let's say it's a different spreadsheet. And every 10 minutes, I have a new spreadsheet. Now, because I want to keep track of what is the order of the spreadsheets, I can store this information that gives me a link, like a URL of if it's a Google spreadsheet, it gives me the URL of the previous spreadsheet. So I store the URL of the previous spreadsheet, and that's how, if I'm on this spreadsheet, that's how I can find all the previous spreadsheets by following these pointers. And obviously, there will be a Genesis record that will have no previous record to it. It will be the first one. Okay, so now let's try to abstract the concept a little further. And let's call all of this stuff let's just call it data, because I'm trying to show you what the block is, and to simplify, I will just call all of that stuff data. And then a blockchain block, what it really is, it's more things, but what it really is that data that I was talking about. It's something we call a nonce, and the hash of the concatenation of the data with the nonce. These three things. Now, what is a nonce? Nonce is just an arbitrary integer number that I can change however I want, and it doesn't really change my whatever transactions are stored in this block, because the transactions are in data and nonce is completely independent. But it's very important, because the reason I have it is that when I change the nonce, even though the data are staying the same, the transactions that we had between people stay the same, the nonce changed, therefore the hash of this block changed. So now Bitcoin or Satoshi came up with this arbitrary definition that says that a valid block is a block for which the hash starts with many zeros. And we'll look at that in a minute in the example. But hashes usually don't start with many zeros. Hashes are, as I showed you earlier, they look very random. So it's very hard to produce a hash that starts with many zeros, because it's unlikely that a hash is so repetitive. So then mining is the process of changing nonces constantly until you find a nonce that makes that new block that you're trying to mine valid. So let's look at this concept right here. All right. Same software, little advanced version of what we see. This is what I call the block. Maybe it has a number. So that's the first block. It's the Genesis block. So it's number 1. Then this is the nonce. And here I have my data. My data could be that Alice sends to Bob 3 Bitcoin. Okay. So, and the hash is data concatenated with nonce, and in this case, concatenated with a block number as well. And this is the hash. Now, is this a valid block? No, because it doesn't start with many zeros. So what do? I go here and change my nonce. 0. No. 1. Doesn't start with many zeros. 2. No. 3. Nope. Okay. So what this software here does is it has a button that calls a JavaScript function on this page that is going to run all the numbers from 0 until it finds a number that makes this hash to have many zeros. Let's press it and see what happens. All right. The background changed to green, and your hash here is starting with 4 zeros. 4 is arbitrary. In this specific case, we just said that we define a valid block to have at least 4 zeros, because if you had more than 4, it would take forever to compute it. And for demonstration purposes, we chose 4. All right, so here's what the software found, that if you have typed the number 14, 11, 16, the hash of the whole thing would have been starting with 4 zeros, and this nonce makes this block valid. So if I was doing it manually, it would have taken us forever, but thankfully the software did it faster than us. So in this case, imagine that when I was in the 14, 11, 14, 115, it would have been not what we want. And then when we tried the 16, all of a sudden the hash starts with many zeros, and then we are very happy we mined the block. This is a valid block. Okay, now let's look at the next concept. The next concept is blockchains. So I want to add the concept of every block contains all the nonce and everything else that I said. But what I'm talking about in this specific slide is that it contains a pointer. It's not anymore a URL that I told you one spreadsheet is pointing to the URL of another spreadsheet, but it is the hash of the previous block. So this value right here is the exact same value as the value right here. So this way you chain the blocks together. So let's look at that as well. Okay, so here's how the blockchain would look. We keep improving our block so that it can have all these concepts that I'm talking about. The first block, the Genesis block, has no previous hash, so let's just put it all to zeros. And it has data such as A gives to B 3 Bitcoin. Now, when you do that, you have to mine. You see, our hash is not all zeros anymore. Let's just mine this. And as you see, the software here helps me by moving this hash from here to here. And now, if in the next block you say B gives to C 0.5 Bitcoin, and then we mine this block, we will end up with a valid block that has multiple zeros here. And if we continue doing that and say C gives to A 0.2, we'll mine this block as well. Now I want to give you the first interesting property of the blockchain and why it makes things pretty secure and what we call immutable. What would happen if actually B comes back and says, oh, you know what, you didn't give me back then 3 Bitcoin, you gave me 4. If I change this to 4, anything I change in this block is going to destroy this hash. And then it's going to destroy this hash and it's going to destroy this hash. So it's extremely easy to detect even a single change in the entire chain of the blocks. So the only thing you need to look if you want to know if a blockchain is valid, you just need to look at the latest block, because that latest block contains a hash of the previous, of the previous, of the previous.
A quick question about what maybe you're about to do this, but the example you gave where you changed the data. Now, presumably, if you mined that new data in that example, you could come up with a hash that would start with the zeros, but then that hash would not be would be different than the pointer in the next block, which kind of breaks your chain and is detectable, presumably, and that's how you prevent. That's how you retain the integrity of the chain. Now, is it the case that theoretically it would be possible to create the same hash with the new data and a different nonce? So is the issue that it's so computationally difficult to do that it can't happen, basically?
It is possible that you can have collisions. This is the next class, but it is highly unlikely. It will take let me put it simply. No one has ever found a collision on SHA-256. And if you find one, not a specific transaction, A to B sends 3 and change it to something else, but any collision, we know they exist theoretically, but no one has ever found even a single collision like that. This is called a collision. So if you find one, you will be very famous, and things will need to change in the world, because we will need to find to improve our cryptographic functions that we use.
Thank you.
Okay, next, let's look at Bitcoin a little more in detail. So how many zeros do we require the blocks to have? Well, the more zeros, obviously, the more difficult for computers is to find the right nonce to produce that kind of hash. And what Bitcoin does in its code, it basically adjusts dynamically this difficulty so that one block is produced every about 10 minutes. So what it does is that every 2 weeks, the Bitcoin algorithm between producing the next block is running a computation, which essentially looks at how many blocks have been, how much time has passed for producing the last 2016 blocks. And 2016 times 10 minutes is about 2 weeks. And if it finds that the amount of time that it took for these 2016 blocks to be produced is less than 2 weeks, it means that the difficulty was not difficult enough, and it increases the difficulty. And if it finds that it was more than 2 weeks, it means that we didn't have enough hashing power in the world, and it needs to reduce the difficulty. So the difficulty is essentially this number D here that you have to divide the hash, so that you can say that a hash must be lower than the maximum hash divided by this difficulty. What I'm really trying to say here is that if a hash starts with a lot of zeros, then that hash is smaller than, in this case, let's say 1 here and everything else zeros. So that's what it means. Is that is there a question here about what difficulty means? It essentially tells you how many zeros are required, and that's why it is defined as 2 to the power of 256, because there's 256 digits in a hash, bits in a hash. So 2 to the power of 256 is the maximum hash you can have. And if you divide that by difficulty, then you basically keep adding zeros here in the beginning. And for reference, today the difficulty is roughly 20 times 10 to the power of 12, which means it's the number 20 trillion. And the resulting block, including the nonce, especially the nonce and the hash of the block, is what people call proof of work, because this proves this very hard work that the whole world did to eventually one of them randomly find such a nonce. And once you have the nonce, then you can very easily check that the nonce indeed satisfies this condition. So let's look at one more concept here, the concept of Coinbase. What is Coinbase? Well, we all know it's a popular crypto exchange in the US. Nope. Actually, Coinbase is a very specific field that exists inside every Bitcoin block, and that's where other concepts got their name from. And what this is essentially, each block contains transactions from person A to person B, person A to person B to person C, and so on and so forth. But there's one very special transaction on every block, which is nobody, Bitcoin itself, the algorithm, no one, gives money to somebody. And who is that somebody? Well, that somebody is always, it can be whatever you want, but people always put themselves. So whichever node or whichever miner or whichever peer, however you want to call them, was able to find the right nonce for this block, obviously he had put their own Bitcoin address in the Coinbase so that they get that amount of newly minted Bitcoin. And in the beginning, the Coinbase was 50 Bitcoin per 10 minutes, basically 50 Bitcoin. And it halves every 210,000 blocks, which is roughly every 4 years. So it has halved 3 times so far, and currently the Coinbase is 6.25 Bitcoin. Here I have the concept of multiple nodes. They're called nodes, peers, or miners. All these words are um, describing the same thing. So there's the Alice, the Bob, and the Charlie. Each one of them has the Coinbase. Each block, as I said, has the Coinbase and the list of transactions. Here's, we can see some transactions. So 10 Bitcoin, I've made it a little too big. Let me make the page a little smaller so that it can be more visible. So in this case, 10 Bitcoin are sent from this person to this person, and so on and so forth. But what's interesting is that every node is trying to set the Coinbase to themselves. So Alice is sending it to Alice, and Bob is sending it to Bob, and Charlie to Charlie, and so on and so forth. So what happens is that when all of them are mining at the same time, they all press this mine button at the same time to mine block one. But let's say Alice found the right nonce for her block first. If you see, if Bob tries to find this, the nonce will be different. For Bob, it's 15,310, whereas for Alice, it's 6,768. Why is it different? It's different because the blocks are not identical. Alice is trying to mine a block that gives the Coinbase to Alice, and Bob is trying to mine a block that is giving the Coinbase to Bob. So what happens in practice is that when all miners are mining a specific block, and whoever finds a nonce that satisfies their block first publicizes this nonce. It's basically sending it to everyone together with the block and all the data of the block that they mined, and then everybody else makes sure that what the claim is correct. And it's very easy because you already have the nonce, and you just need to say here Alice, and then Bob checks and sees that Alice says the truth, that this is a block that is valid. And then what happens is that every node applies this to their current copy of the blockchain, and every node makes the decision that we are done now with block one. Let's all start mining block two, block three, block four, and so on and so forth. And then what happens with block two is a similar process. You get everyone is trying to mine for themselves, and whoever finds it first, let's say in this case Bob found it, found a nonce for this block, and then Bob announces this to the world, and everybody tries it and update the data with what Bob said, and voila, everyone sees that this is valid, and then they all move to the next block. And remember, the difficulty of Bitcoin, how many zeros we need to have here, is so high that it takes the whole world computing concurrently, like trying different nonces for just one node to find a nonce that is valid every 10 minutes. So it's not like something like here that finishes in a few seconds. It's something that takes 10 minutes. So at the end of the block, when the block is announced, everybody, and I will explain in the next lecture why, an additional reason for that, but everybody has an incentive to consider this block done and move on and start mining the next block, so that maybe hopefully the next block is the one that they're going to win, rather than them keep mining an old block that everybody, the whole world moved to the future of the blockchain, and they're still mining the old one. They immediately abandon that block and move to the next, consider it done. Now, another concept that I want to say here is what someone who asked a question earlier mentioned, is that obviously the blocks are not having just data, they have structured transactions, and there's more information that is missing here from the transactions that I will explain in the next class, the cryptographic signatures specifically. So what else do we see here? What we see is that at the Genesis block, we did not have any transactions, and the reason is because no one had Bitcoin yet. So no one has Bitcoin, no one can transact with it. So what happened is that the Coinbase comes here and gives to Alice or Satoshi in our real world example, 50 Bitcoin, so that then that Satoshi person can give it to others, and then the whole economy can be ignited and take place. Let's look at the real Bitcoin block from earlier this morning. Interesting concept. I told you miners sometimes are unknown. How can we trust them? We'll talk about it next class. This is the current difficulty. This is the exact number. That's what I said. It's 20 trillion. This is the nonce of that block. It's what's that 1.5 billion something. And this is the block reward. This is the Coinbase, 6.25 Bitcoin. And there is also tips that people give in order for their transactions to be included in the block. So if you have more transactions, each block can have a certain number of transactions in it. And if there are more transactions in the network that need to be executed than the ones that can fit in a block, then what ends up happening is that essentially people who want their transactions to be included in the next block, they including a blank check pretty much that essentially the miner can cash out to themselves. And what this does is it allows the miner who is including this transaction into the block to take this tip, and this gives miners an incentive to include transactions with higher tips versus transactions with lower tips. So this way, if there's more transactions, every miner is ordering the transactions by tip and is including the transactions with higher tips because they have financial incentive to get the tips. Now, let's look at how the Coinbase reward evolved over time. So in 2009, it was Satoshi and his two friends. The Coinbase was 50 Bitcoin per 10 minutes. 2012, it halved to 25, 2016, 12.5. We had a halving in 2020 last year, and now we are at 6.25 Bitcoin per Coinbase. And according to this graph, you see it's like a logarithmic, it's decaying very fast. So in 2140, roughly, we're expecting that the Coinbase will be zero, because at some point the algorithm says it becomes zero. It's like so small that it becomes zero. And at that point, the expectation is that the transaction fees, those tips, is going to be what the incentive is for miners to continue mining. Let's look at the same graph in another way. So for the first 4 years, the Coinbase, which is essentially the emission rate, the rate in which new Bitcoin comes to existence, was growing at this rate, which means that within the first 4 years, about 50% of the entire Bitcoin was already minted. And then an additional 25% was minted here, an additional 12.5% was minted here, and so on and so forth. That's why we say that Bitcoin is a deflationary currency, which means that there is a maximum amount of it, and it's kind of like gold or real estate. The area of the earth is set; it doesn't increase over time, and therefore it is bound to be deflating, meaning that it increases in value over time. Whereas fiat currencies, most of them, or if not all of them, are inflationary, which means that every year more of it gets minted. Now let's look at the hash rate. So what is the hash rate? So in the beginning, people were mining with their computers, and they were able to produce one hash every so many milliseconds. But these days, the customized hardware is used, which is initially it was some chips called FPGAs, and now very custom chips specifically for computing SHA-256 hashes in order to increase the efficiency at which you can hash Bitcoins. And if you take everyone's in the world, all the Bitcoin miners in the world, computers, and sum the amount of hashes per second each computer can do, then this is what we call the hash rate. And this is these days measured in exahashes per second, but no one knows what exahashes per second is. So the maximum number we're usually accustomed with is terahashes per second. Tera, it's like, and that's why this number here is 143 million terahashes per second. So let's look at the history a little bit. So in 2011, it was 0. Like that's somewhere here. It was 0.1 terahashes per second. Then it went to 10, 20, 10,000, 300,000, 800,000, 2 million, 15 million, 42 million, 105 million last year, January. And this January, a few days ago, it was at 143 million terahashes per second. And this is the difficulty. If difficulty is following a similar graph as the hashes per second, because the more the difficulty, the more the hashes per second, the higher the difficulty needs to be adjusted to be. So it's a little bit of a delayed version of the other graph. Okay, so I think that I will stop right here for today, and for the rest of the class, I will take questions so that we can talk about these two important concepts more next week. I think there will always be people who will be taking care of their private keys and they will not be losing their Bitcoin. But anyways, I think what you are alluding to is that as long as you keep dividing the currency, then the divisions of it become more and more valuable in a way. But also another answer is that maybe not all cryptocurrencies, all is to cryptocurrencies is Bitcoin. Maybe there's a lot different properties that people need, different utilities that people need to implement on top of cryptocurrencies. So I think the technology is here to stay. It's as we will see next class, it's the first time in history that we are able to not having the need to trust some organization in order for us to make specific actions, such as transacting with our funds or storing our funds. And it's also the first time in the history where you can have self-sovereign identity in a way. So because we will talk about private keys and public keys, if essentially the only person that can take Bitcoin out of your Bitcoin wallet is whoever has the private key, which is something like a password. And you can prove that you are who you are just by having the password. So in the past, in any other historic event since the beginning of time, there is either I'm living in a village 1,000 years ago that and then everybody else in the village know who I am, and that's how I can establish that this I can give you this piece of land, and then everybody is a witness, so your piece of land is yours. Or in the recent years, we have to use passports or credit cards or intermediaries. So the intermediary would be in the passport example would be a country that issues the passport. So then everybody trusts that the country gives one passport to one person and the passport is legitimate, or the bank institution, which basically gave you the credit card or the debit or the bank account number, and then people have to trust. But with this technology, it's the first time that that you can have this self-sovereign identity, and I think there is a lot more innovation that will happen because of this property. We have a lot more things to invent because of that simple thing.
Thanks.
There's a rule that is the longest chain rule. So whichever there could be forks of Bitcoin, and But there's always one fork that is longer or has much higher difficulty than any other one, and that is the official Bitcoin ledger that people are following. That's one. That's one answer to your question. And the other answer is that it is very possible that different peers include different set of transactions in their blocks. That's perfectly fine. But in the end of the day, one peer is going to find the nonce. It's going to essentially mine this block. Then whatever transactions this peer selected, these are the transactions that that will be recorded by everyone else. Because this person is going to say, here's my nonce. The nonce is going to come here. And it's going to say, here's my Coinbase. Coinbase is going to come here. And then he's going to say, here's the list of transactions that I had. So the decision is made and we're all moving forward to the next block. And there's multiple incentives why you want to, why everyone moves to the next block, which we will see. What you're saying is possible, and it's the case where Alice and Charlie find the nonce for their block, basically mine their block at pretty much exactly the same time. That is possible. And at that moment, both of them are going to start broadcasting the block. So what will end up happening is just a network delay. Whomever's block reaches more people, more other nodes earlier than another, more other nodes will basically adopt it, and they will start moving into the next block. And when they receive, if Alice arrived first, and then these nodes are already mining the next block, if they receive Bob's or Charlie's block, they will say, no, I'm actually already minting the next block. I'm mining the next block. I don't care. Basically, they will recognize this as a fork, and they will keep doing what they are doing. If, on another hand, though, let's say this is also possible if there was a network split. If the entire internet of a specific country was down for an hour, then all the miners of that country would be basically mining by themselves and making decisions and creating blocks. And all the miners of the rest of the world would be creating blocks as well. So in this case, during that 1 hour, because the miners of that country are not that many, they are fewer than the rest of the world, let's say, excluding a certain country, then they will have produced not by 1 block every 10 minutes, maybe they have produced by 1 block every half an hour. So they will have 2 blocks produced in that 1 hour. And the rest of the world will be producing, maybe because they lost the country, they will not be producing 1 block every 10 minutes, they're 1 every 11 minutes. So they will have produced about 5.5 blocks. So in the global version, the blockchain has 5 more blocks. In the other version, it has 2 more blocks. So that blockchain is smaller. So everybody is just following the longest chain, the one that has the more work, which we will see in the next class exactly what this means. So yes, forks can happen, and there is a way to resolve them. That's why there's a property of safety and liveness. So Bitcoin, and there is a theoretical theoretical proof in fault-tolerant distributed systems that you can't have really both. And Bitcoin is guaranteeing liveness, which means that no matter what, even if there's an atomic bomb, 90% of the world is gone, the remaining 10% is going to keep producing blocks. But so liveness, it's going to be live, it's not going to block, but it has the problem that it might not be safe. So in that situation we had where the country was disjoined by the rest of the world, they will have a different version, and that version will vanish after the whole network reconnects. So Bitcoin doesn't guarantee safety, but it guarantees liveness. Other cryptocurrencies guarantee liveness, but not safety. For example, banks always guarantee safety versus liveness. So if there is a chance that your wire transfer might be lost, then the bank stops, says, sorry, we're down today. The server is not working. Just come back later. We can't send wires. That's the guaranteeing safety versus liveness, but Bitcoin doesn't guarantee that. And I think we are ending in about 5 minutes, so we have time for a few more questions. Keep shooting. As a miner, what you do is you basically come and put your name here. You're a miner Alice, and you put your name here, and you press the mine button, and you keep pressing the mine button for the rest of your life. And I guarantee you that you will never get a block, because it's so unlikely that you get a block. But what people do is they get a lot of computers together into a mining pool, and that's how. And one of the people in the mining pool get the block, and then they split the Coinbase together. But this aside, that is one way. That's how people. That's what people do. They're putting their name in the Coinbase. They click mine, and they hope that they will get the Coinbase. Now, the second way that they get Bitcoin is because some of these transactions contain tips. And so they both, whoever mined the block, found the right nonce, is going to get the Coinbase and the tips. And that's the second way they do. Now, what happens is that that Bitcoin goes into the account of whomever, Alice in this case. And then what Alice can do is Alice can create transactions, send that Bitcoin to an exchange, a cryptocurrency exchange. So if you look at the way how many Bitcoin belongs to what address out there, to what wallet, you will see that the largest holders of Bitcoin and most cryptocurrencies are cryptocurrency exchanges. So what happens is that Alice here would open her mobile app. She will go to Coinbase. She will say, I want to transfer my Bitcoin from the blockchain to my app. And then the app will say, oh, okay, great. Please send it to this address. And then Alice is going to go to her favorite wallet, which is going to produce basically a transaction like this. And she will say, okay, I want to send this many Bitcoin that I have to the cryptocurrency exchange's wallet address that they specifically gave me, and make the transaction. They submit the transaction on the network. Potentially, they include a fee or a transaction tip. And after several minutes, maybe 10 minutes or 20 minutes, or whenever the transaction is included in a block, then the transaction happened. So when it happened, then they go back to the mobile app that has or the website that of their favorite cryptocurrency exchange, and then after a while, there is some software that is running on the exchange that is validating that this transaction actually arrived, and then it increases the balance of the Bitcoin for that person on the balance of the crypto exchange. Now, when most exchanges, unless they are decentralized exchanges, which is a different kind of thing, but most major popular, well-known exchanges, they are not decentralized at all, meaning that they are the same concept as any bank. So you trust them with your funds. So you don't have any private keys. You don't have any of these things that we'll talk about, any of the guarantees that we'll talk about next class. So you just trust them with their funds. Their funds, your Bitcoin corresponds to a database record in the transaction, and then you can order transactions in the same way you would order transactions in a stock exchange. It's like just normal, plain old server stuff. It's nothing to do with crypto. Yeah, Bitcoin has a very specific scripting language that you can apply. So you can do very simple things such as multi-sig wallets and things like that. But what the breakthrough of, well, let's say, the innovation of Ethereum is that Ethereum's programming language is completely generic. So you can do almost every program that you can imagine. You can't do input-output stuff. but you can do any program that you can imagine. Having said this, the whole Ethereum computer is comparable to an extremely slow computer from the 70s. And the reason it's not like, the reason why this is the case is by choice, because that computation is being replicated across every single node. So you don't want it to be running machine learning algorithms. You want it to basically make sure this smart contract, when you send it funds, it responds this. Like you can create an escrow smart contract, or you can create your unit swap, or what you want to create on it. But you can create a complex algorithm.
Thank you. That's very helpful.
Okay, cool. Well, thank you, everyone. We'll be on Slack, and I'll see you again next class.